Well, because you could you can actually pay off.
So I actually paid off half my system my daughter.
Yeah.
That was good.
That's nice. Yeah, managed to stay so far working part-time and then full-time. I guess it's more like we actually get some relationships.
That's awesome. Yeah, like I was exactly. So like San Diego, I was like taking an interview every day, and every drivers to ask me, like, you're doing an internship? He was like, you can pay for it. I'm like, yeah. What? I'm like, is that a foreign concept here?
That's
They're like, I'm doing law, I don't get paid.
Okay, how's it going? It feels like a long time since I've been here. It has been a long time since I've been here. Couple of things I think to talk about. One is, I really did miss you, so I'm glad you're back. Sort of. The other thing is, sorry to be late, but now, my office is now, instead of being really close, up on the research park, we actually moved offices this week downtown to the Gateway Mall of all places. So now I have like a 20-minute commute just to come here down there. So I didn't realize it would be so long. Sorry to be a little late. If you want to come visit me over there, you can. There's a cool rock climbing wall. If anybody ever, maybe you're all too young for it, but back when the Olympics came in 2002, you guys were all probably in elementary school and stuff. Dick's Sporting Goods, the Gateway Mall was built. Dick's Sporting Goods came into there. It's right across the street from the what's now the arena, and it was this like massive, huge retail space, and they had the tallest indoor climbing wall in the U.S. at the time, and now that's our office. So, if anybody doesn't know the history, City Creek came in. How many years ago was City Creek built? Maybe 5 years ago or something, 4 years ago. Not too long ago. And then basically all of the stores from Gateway moved, 5 blocks east, and then there was nothing left of the Gateway. So the Gateway is trying to kind of rebuild itself, and one thing they're doing is trying to attract like tech companies to come there and have their office space. So we're basically one of the first ones to move in down there. So it's pretty cool, but it's a longer drive. But probably the thing that's most on your mind is project proposals. So, couple of things. One thing is I think I made a mistake by not assigning any points to it, because all of a sudden I think now all of you who are conditioned to just do things for points and nothing else are like, I need to turn that in. So that's my mistake. I now know that points are needed to encourage turning things in. So I don't think I'm going to change it this time, but maybe next time around I will require points. But the point here is to get your proposal in so that I have a chance to look over it and can make comments on it and help you get off on the right foot so that you're not wasting too much time doing things that maybe are not as effective. That's the point. If you don't, it's true that there are no points associated with it, so I don't know what to say about that. I'm not going to change it now, but I will probably in the future. So this is my first time using Canvas, and it looks like, so this is a group assignment, and we don't have the groups like in Canvas, but apparently like with this assignment, I had it turned on where like you form your own groups like while using Canvas. Has anybody had experience doing this? Anybody? No? This might not go so well. This? Maybe? Well, what was the experience? Could you actually form a group on Canvas?
Yeah. Yes, you can do that. You can do that.
I don't know how that works with turning stuff in is the only thing.
What do you mean? Like, wow, at the same time?
You can form groups, but I don't know how that works with assignments.
Yeah, okay. So the way this looked was, and this may not be the case, so maybe somebody try it who's diligently got the proposal already finished. But it looks like for this assignment you can both, so you can turn something in, but also specify like which group you're part of. So that may or may not work. So, yeah. I don't know. Hopefully that'll work. If it doesn't work, we'll figure something out. You only need to turn in one of these proposals per group, so that's probably like what everybody's wondering about, but I don't know. I honestly have no idea. So try it. Hopefully it works. If it doesn't work, we'll figure it out. Good. So how many people are like, I'm going to have it turned in tomorrow? How many people are like, I don't even have a group yet? Okay. How many people are like, yeah, hopefully, this is meant to be good. Hopefully it is. There've been a couple questions. I think I've answered them before in class, but I think it's worth saying again. This is not meant to be some like amazing research project that you could publish in a conference or a journal or something. This is meant to be like, hey, I learned some deep learning and I'm going to apply it to something. And look, it worked, or look, it didn't work. So that's really what it's about. So I hope no one's feeling like extreme pressure to try to impress everybody with like the most amazing problem, data set, techniques. The idea is not to just repeat something that somebody's already done. You know, it's like to take ideas that you've learned here and maybe just apply it to something a little bit different. And that's that. Okay. Any questions about any of that? No? Okay. Yes.
So we have $50 book credit.
Yes.
So how can we get it?
Yeah. So I do have coupon codes for anybody who wants it. So I guess probably the best thing is if you want it, just like contact me through Canvas and I'll send out the coupon or the code, and you can just add that to your Google account. I'm hoping that for most things, like collaboratory should be enough. I mean, you get one GPU there, but like if you for some reason decided you needed something more serious, which maybe you will, then you do have $50 worth of credits. That may not go very far, but that is there. So it's up to you. Just let me know, and I'll happily send out the codes. We started playing around with Google TPUs. You know what those are? Have you heard of TPUs? Yeah. Yeah. So GPUs make everything way faster than CPUs, and now TPUs make everything way faster than GPUs. Like way faster. Like it's pretty awesome. So they're expensive still, but we started playing around with them. Wow, they are fast. Things that like would take us a couple days to train on like lots of GPUs would take like an hour to train on a TPU pod. There's like a lot of like TPU cores in that. That's like I think 196 or something like that. So, anyways, it's pretty expensive, but pretty cool. I think you could probably try to use TPUs if you wanted to with your Google Cloud credits, but it would go pretty fast. All right, enough of that. Shall we get going? Oh yeah, and then in between all of this, we've had, so, is Alessandra? I don't see Alessandra today.
No, he's not.
Yeah, okay, so anyways, you got Dave again teaching you about recurrent neural networks. And then the idea was to follow that up with a part 2 of recurrent neural networks, which actually I'm going to be doing today because I wasn't able to attend on Thursday, and then Alessandro filled in, and he just felt uncomfortable doing something that was planned to be done in a couple of weeks. So we're a little bit out of order on that. I apologize. And in between that, we had the unfortunate events that canceled classes on Tuesday. So we're a little bit off, but this is like one of those fun classes, right? It doesn't really matter what we do. So anyway, hopefully with that spirit, you're okay. Okay. And this is all recorded, so yeah. Okay, here we go. Now. Okay, so this is going to be our part 2 lecture. So who enjoyed learning about recurrent neural networks? Raise your hand. They're pretty amazing, huh? The things that they can do. Did you guys watch some of the Sunspring movie? It's pretty cool, huh? Dave told me that you didn't watch the whole thing because he thinks it was so ridiculous he couldn't possibly watch it. So, did anybody actually go and watch the whole thing and do some background reading on it, what it is? It's pretty cool, huh? And how they got Thomas Builders to do it, I don't know, but he makes it really pretty believable. Not believable, but gives some legitimacy to it, not just a couple of students doing a video. How about the part where the eyeball comes out of his mouth? That's actually in the script. It says eyeball comes out of H's mouth. Yeah. Statistically, that should happen in a sci-fi. All right. So recurrent neural networks. So up until a couple weeks ago, we've been focusing on convolutional neural networks whose job is to capture spatial correlation. So spatial arrangements, local correlations between pixels in an image, and then through levels of the network, layers of the network, to sort of create longer range spatial correlations. And now recurrent neural networks do this for a different type of data, for time series data or sequential data. So the recurrent neural network, their job is to learn temporal or sequential correlations. And we won't spend time doing it today and probably in any of the lectures, but at least somebody asked me about this. You can combine the two so that there's you have convolutional recurrent networks that are learning both spatial and temporal correlations so that you can classify videos, for instance, and things like that. But I hadn't planned any lectures, although somebody asked about it, and I don't know, maybe because again, it's one of those fun classes, maybe I'll throw it in, but anyways, just know that that's these two things aren't mutually exclusive. You can do them both together, and that's pretty powerful. So there's lots of ways to formulate recurrent neural networks, in terms of in terms of inputs and outputs. So really, really flexible just in principle. Yeah, hopefully you guys went through these. These things at the beginning are more let's see. What sort of things, I'm trying to think about what you talked about in that first lecture. You looked at examples of many-to-one type things where you have a sequence of, some text, and you're trying to say this is, I don't know, maybe has a certain sentiment or it's classified in a certain way. And these many-to-many ones are for doing translation. For translating, say, from one language to another, or question answering, here's the question, here's the answer. Yeah. There's this basic idea can be used to do a lot of things where you're trying to, again, learn temporal sequential correlations in the input, and possibly also wanting to capture those in the output. And we train these things through exactly the same means. We use gradient descent, stochastic gradient descent of some form. And the backpropagation works, and we use backpropagation again to do this. It's just that we have not only do we have all the things happening within each of these units, which is usually again linear transformations followed by a nonlinear activation, but then you also there's some notion of this temporal sequence, and so the backpropagation has to propagate through time. And so when you build these computation graphs, not only do you have a graph for each one of these cells, but you think of this as this unrolling sequentially and all the gradients have to be propagated through those parts of the graph. So they can be, even though they can be kind of simple to write down, actually in practice these can be pretty complicated and can be time consuming to train. Okay, so something interesting that was done by the people who actually put most of these slides together that I'm using here in this class was this workshop back in 2016 at iClear about like training very simple character RNNs. So these just character-to-character RNNs, just like from a sequence of characters predict the next character. So very, very simple types of like text generation models. But then like trying to go through the networks they were training and look at different of the neurons or the units in each of these, the cells in each of these, and then to say like, what are they learning to do? And there's actually an interesting blog post that's also on this very same topic called from Andre Karpathy called The Unreasonable Effectiveness of Recurrent Neural Networks. That's also a great read. But here's some of the things that they try to do. So they try to go through here and say like, as we feed these different characters sequentially into this network, they would focus on like a single unit and say like, is it firing, or is the activation large or is it small? And then they sort of color this so you can see. And what they found is, while some of the neurons or the units in the network were maybe hard to interpret, there were some that were like totally easy to interpret. So for instance, you have this one that appears to be like a quote detection cell. So you are feeding into this. Let's see. Yeah. So this starts with a quote. So this appears to be active while you're inside the quotes, and then as soon as you finish the quotes, it deactivates. And as you start the quotes again, it activates and it deactivates. So it's just sort of keeping state, like open quote, close quote, open quote, close quote. And that's kind of interesting, right? Because what it's saying is that like it's learned that quotes come in pairs, and there's probably other parts of the network that are deciding what should be generated in between these quotes. But the fact that there's something in there saying like quotes, where open quote and a close quote is pretty cool. And again, because these things are learning, in this case, like the statistics of language or written language, this seems like an obvious thing that you would expect to find. Here's another one that's pretty interesting. So there's another neuron that just is keeping track of your line length, and then realizing that you're going to have to like do a new line or a carriage return here. So it's like blue, and it's like, oh my gosh, get in the line, get red, and then return to the other. New line, come back. So that's sort of whatever this was trained on, it's learned that it has to insert a new line every once in a while, and that's interesting. Here's something that was like trained on. I think you probably went to the example of like the Linux kernel. Like they train these character models on the like all of Linux, like what's in the GitHub repo. And so you have neurons that are keeping against the state of like opening and closing parentheses in these conditional statements. So something that's like paying attention to what's inside, like what is the condition. So that's cool. Here's another one that can code for keeping track of comments. Here's another one for keeping track of depth in the code. So again, like when this model is trained, all it's trained to do is to take a sequence of these characters and then learns to produce the next one. Right? So it's supervised by saying, given the sequence, it's trained to say like, this is the next one. But as a result of this, you can look, you can go through and you can see in the network that actual individual neurons or cells, as it says there, are learning to do specific statistical properties of this, which is just interesting that you can see this. So powerful, right? The power of being able to learn lots and lots of data. text is interesting because there is lots of it like open, like available for free. Like you can download all of Wikipedia, I guess, and you can train on all of it that way. You can train on like all of the books in the public domain. You can download these things and you can train on these things. So there's lots and lots of like cool examples like this because there's just so much data available. Okay, so let's look at some additional applications of recurrent neural networks. So we've kind of seen this a bunch already. In fact, if you started on the homework, you'll see that there's actually like an image captioning problem there, very much like this. So how does this work? How in these recurrent neural networks do we actually include information about the image and have that affect what is produced in the recurrent neural network? So let's look at an example of this. So these things do have two pieces. They have a recurrent neural network, and this is not like what I was saying before, where you're like learning to classify. Like this isn't necessarily like the convolutional recurrent neural network put together, but this is sort of like there's two of these separate pieces, but you use the convolutional network to produce a representation of this that gets fed in as part of the state to those recurrent neural network. Okay, so how does this work? So we start with like any standard model, something like one of the VGG networks that's pre-trained to like just classify stuff in an image. And instead of going all the way to the classification step, we actually remove the softmax layer and, like in this case, the fully connected layer to produce the dimension 1000 representation. We go back to say like the representation of size 4096. So we use this network right here to featureize this image. We run inference on this image, run it through the network, and down here we get this vector that represents this image. Okay? So now we have a vector representation of the image, and what we want to do is we want to feed that into the recurrent neural network. So let's see. So with these networks, you have to do a little bit of like cleaning or pre-processing of the data, where you want to have like clear start characters and end characters, so that you know when, like it knows that it's starting, and the network knows that it's starting, and also it can produce the ending of character, terminal character. So you start with one of these, and then, like you've seen, like in very simple neural networks, you have like the hidden state that you're kind of you're keeping track of and feeding into the subsequent states. You have this combination of, so this is what you would have before. So this is like kind of the standard thing. You'd have a weight matrix associated with the hidden state, and a weight matrix associated with the input, and then you do this multiplication, add them together, apply your nonlinear activation, and you get this update to the state. And here now, what you just have in the simplest case, what you have is again something linear transformation for the input, linear transformation for the hidden state, but now you have one more linear transformation for the representation of the image that goes into this, and then you apply your activation, and now you have this update to the hidden state. And when you're training, you would train in this way. These would now be how your layers are put together. When you're doing, like in this particular example, after it's trained and you're actually doing inference, you want to test on this. You would then sample from the output. So this would be some sort of distribution over your vocabulary, saying, what's most likely to be output here, and then that would become the character that you feed in. That would be like your X that you feed into the next stage. And then you just keep doing this. You have your hidden state from the previous time step, and you just keep doing this. until you get to your end token, until you sample the end token, and then you're done. And it seems maybe amazing, but that's really all there is to it, and you can train these things to like learn to tell you that there is a cat sitting on a suitcase on the floor. And other things, like a white teddy bear sitting in the grass. So it's pretty amazing, right? There's not a whole lot, I mean, so there's a whole lot that goes into training a convolutional network on ImageNet. It's like, you know, we spent a lot of time thinking about it. Once you have that, you can now just use those representations for these images and then just input these into these fairly simple recurrent neural networks and get like really impressive results. Of course, you need data for all that. And of course, every once in a while, these things don't do so well. And we've seen examples a bunch before. I like this one. The woman is holding a cat in her hand. There is no hand in that picture, but there's definitely something furry. Yeah. I mean, what's really interesting about these examples is like you can see why they kind of went this way, right? It's again, it's only as good as all the data that, like the training data you give it. Like this, it could probably, if you gave it more data around like models wearing fur coats, you know, in funny poses, it would probably learn to like say, oh, that's a model in a fur coat with a funny pose, right? So it really isn't a limitation of the networks at all. It's really more a limitation of like what's in the data. Yeah.
How do we evaluate the performance of this model? There isn't a correct answer.
Well, there is, right, so like if this is your test data, then you do have a caption associated with it, right? Because like your training data had the image and the caption, right? So you have that for the test set as well. So you do have something to evaluate it to. But it's kind of funny to think that like, because language is like a many-to-one map in terms of like many ways of saying like the same thing, right? So it's, you know, you can evaluate it in terms of like, did it get exactly the right thing? But that wouldn't be fair, probably. And so coming up with other ways of doing that are quantitatively are pretty hard to do because like who's to say what is like the main content in here? But yeah, there's like, I guess there's not really like an awesome way to do that. There's just like lots of looking at things and hoping that it's good. There are some ways of quantifying this, like having additional models that can parse these things and, you know, decide that there's like relationships between, you know, a woman and a cat in the hand and things like that that you can sort of map between the two captions, but I don't know that that's always, I don't think that that's very common to do. I'm not really sure, to be honest. But yeah, it's a good question. A lot of this is just like humans looking at this and going, hey, that's not quite right. But most of the time they're like really instructive. It's instructive with these things because you kind of can see why it got it wrong. And if you really needed to correct it, you could imagine thinking about how to augment your data to correct that. But really, no one really cares to caption this the right way, right? Probably not. Let's say like if you wanted to caption something like medical images with like a diagnosis, like that would be, you'd want to be a lot more careful. Okay, so another take on this that's really interesting is adding in this idea of attention. So this is also one of the things that near the end of the course we could spend some time thinking about attention models. But what we have here is we're going to add something to the networks that is going to attempt to attend as it's generating the caption. it's going to attend to certain parts of the image while doing so. For instance, like when it produces bird, it will tend to the pixels that are bird-like, and when it produces the water, it will tend to the ones that are water-like. And this actually improves the ability to caption, like because you're like requiring the network to say like attribute this to pixels in the image. But it adds a bit of complexity. So this is what it looks like. So you have your images and you have your network that featurizes these images. But instead of like featurizing to a constant length vector, you featurize to a matrix. That's basically like, think of it as like a coarse representation of the image. And then that feeds into, like in the other models, that feeds into your hidden state for your RNN. So how this works is you're going to learn from each of these states, you're going to learn two different things: distributions over locations within this matrix here, and then you're also going to learn your vocabulary distributions to say which word you should choose. And there's this feedback in these that takes these location, like this probability of what location it's in this original image, and it weights it by these features d, like this, or size of length d, and produces another latent variable z that just is like a representation of where in the image the thing that we're about to produce, like the word that we're about to produce, is. And with that latent representation, you then feed it the first word, and you say what should be. It produces now your distribution for what should be the next word, plus another prediction of the distribution for the locations it should attend to, the model should attend to, when it goes to predict the next word. And that's actually really complicated, I guess, to describe here in words. But instead of it just being a typical straightforward RNN where you're just only predicting at each step what word should come next, you're also predicting which locations within this image should be attended to. And you just keep doing this until you've finished off the caption. And what's cool is you get things like the following. Yeah, actually I wish this would have come after. Let's look at this first and I'll come back to this. So you get something like this. So a woman is throwing a frisbee in a park. So at the point of the model where we were predicting the next word for frisbee, the attention, this is we try to overlay this idea of attention onto the original image by like in white sort of highlighting which pixels are being attended to. And what you see is that this frisbee, like the pixels around the frisbee are being highlighted. They're being, you think of this as just like a 0-1 map basically, and just, you can see that there's like a little bit of activation on the people, but it's highly activated on the frisbee. Or like a dog is standing on the hardwood floor. So it's showing you like I'm using these pixels to decide to produce this next word and so forth. And this is pretty interesting because there is no, when you're supervising this, it's not like you have these pixels to supervise with. Or sorry, the attention map to supervise with. It's learning to do this as part of the end-to-end training, which is cool. So I think this one's really illustrative here. A giraffe standing in a forest with trees in the background. So notice how, in doing this, like all the pixels surrounding the giraffe seem to be attended to, but the giraffe itself is not. Which is cool.
So how does it learn to do that, I guess, if you can't give the images? So these are the pixels.
Yeah, so you're supervising, so there are loss functions associated with these distributions here, but these distributions, they just get fed back into the network through this latent variable here. So it's just like an emergent property of the training. There's like it's coming from these losses here. Like so like you're optimizing on those losses, but because there's this additional feedback loop inside of it. Exactly. It's learning to do that.
Can you go back for the B? There was something.
Did you say go back? Sorry.
Yeah,
Go back. Over.
Yeah, I was getting over the B and then calculating the weighted
The representation of the
what are
z is equal to sum of the here.
Yeah. So these P's are the probabilities for the locations within your image, and these V's are the features. So like the V's are basically like the entries within this matrix. So think of it as like each one of these is a vector, and this is the probability of that vector, and it's just weight. It's like a weighted sum. It's like you're doing a linear combination of the rows of this thing, weighted by those probabilities. So like that's not enough detail probably like to implement it directly from the slide, but like that's the idea. Because right at this point, what you have is you have a you've already passed this image through a convolutional network, so you have this like latent representation of it.
so I guess my understanding is the L or the partition in this case of the 9 cell is the partition of the whole image.
Yes, right, exactly. So like the L here is referring to like the rows here in this representation. So yeah, so that's pretty cool, right? Because it's like you're not supervising that piece of it, and yet it learns to do this because you're supervising it by the just the word. You're supervising the word distributions, and each one of these is just a simple softmax, right? Like you probably talked about this when Dave was here, but like when it says distribution of the vocabulary, that's just like it's a softmax output, so it's a distribution over each of the words that you possibly could predict, and at test time you're sampling from that, but when you supervise this, you're supervising it with the one-hot vector that is like this word in the vocabulary. Yeah.
Are the weights like your Z1 in that picture? Are those network parameters?
Yeah, so they're not network parameters. Like, think of this as like when it goes into here, there's another weight matrix that multiplies this vector. That's added to the weight matrix multiplying this vector, and all added together, and then a nonlinear activation.
But those weights get updated, like they're learned.
Well, they're learned in as much as like you are. Let's see. So there's a weight matrix that you're multiplying this z by. That's the thing that's learned, right? But like what these actually are determined by the weight matrices everywhere else. Does that make sense? Yeah, it's like lots of loops. It's hard to show it in this picture. Let's see. So let's go back to this. So the thing that's making the z is the probability distribution that's coming out of here. That's these p's.
Yeah.
That is that is dependent on learned weights.
Oh,
Right.
I see, okay.
This V is not dependent on any learning. Like this is like a, we are running inference on this image and then we're getting some sort of fixed representation of it. So this is not learned. The P is like learned because it's the output of learned functions. And then then that Z is like the combination of them and then it just feeds in. So like, yeah. And then something multiplies, some learned matrix then multiplies those Z's and so forth.
It gives you the next distribution.
Yes, exactly. And so on. You can use these exact same networks to do cool things like visual question answering. So I think I pointed out at the beginning, like you can use these many recurrent neural networks to do to take in both the image and the question, and then output the answer. So, like in these examples, what endangered animal is featured on the truck? I mean, I don't know. Like, they got it right apparently. There's obviously a baldino on there. Where will the driver go if turning right? So, this is kind of, I never really looked at data sets like this, so it seemed really weird because, how many, look at this one. When was this picture taken? So during a wedding, during a bar mitzvah, during a funeral, during a Sunday church service. I guess, I don't know. Thinking about the training data for this is interesting. But I haven't spent a lot of time on this, so I don't really know much about really how this is put together. But the point is that these same techniques are used to do this kind of stuff. So there you go. And you can also add the attention part to visual question answering. It could tell you, why, it could tell you why it answered the question the way it did, in the sense of showing you which pixels in the image were important for that. Recall this is kind of like saliency, right? We've used saliency maps to say this network, excuse me, this network classified this image in this way, and then we use saliency maps to sort of show us which pixels were most important in that. This is kind of like that, but it's different in the way that we approach this. This actually is done as part of the learning, and not just something that we do after learning, which the saliency maps are. This is also pretty interesting. Maybe we'll spend time a little later in this course talking more about attention, because attention really is interesting. It's making lots of really interesting progress in certain problems. So much so that there are models that exist now called transformer networks that aren't recurrent in nature, but can perform as well as recurrent networks. And they simply just attend to, and not only that, they can they're even better than recurrent neural networks in the sense that they can learn longer temporal correlations. They're pretty interesting. Okay, so let's think a little bit more about the mechanics of these things. So here's just a vanilla recurrent neural network. So again, there's some kind of input at step t. There is the previous hidden state. And the way that a vanilla recurrent neural network works is both of these are multiplied by weight matrices. You add all that up, you apply entry-wise, feature-wise, nonlinear activation, and then you get this updated hidden state, which then you would use for the next part of the network, of the input sequence. And you can see here, this is just rewriting that in terms of a larger matrix W, including both of these matrices, and this is vector of vectors. So it's really pretty simple, right? It's just linear transformation, hidden and state and input, and then entry-wise activation. So the computation graph looks a bit like this. So like one cell in this recurrent network would have this kind of computation graph. So this just says stack them together, multiply by W, apply tanh, and there you go. You have the next steady state. So pretty simple. Gradients then flow in the opposite direction, and what happens is when we do the back propagation, because we have this matrix multiplication on the way in, we will actually have it on the our gradients will have this W. Will be multiplied by this W. Well, and each cell will be multiplied by this fixed weight matrix. Well, sorry, I didn't mean to say fixed, but this at the time t, this whatever this weight matrix is, and that actually kind of poses a problem because who admits to like being good at linear algebra? Hey, one person's good at linear algebra. When I was an undergraduate, it was the one math class that I got a D. And it made me so like embarrassed that I wanted to take it again. But like, they were like, "Don't take it." Just like keep going, it'll be okay. And it was okay. It was fine. I think. But anyways, what happens when you keep multiplying a matrix by itself? What happens? So like you have W. So let's see if I write this down. So we have like our matrix W, and then some vector X. So now I multiply this by W again, and I multiply this by W again, and I multiply it by W again, and so forth. Dot, dot, dot. What's happening here to this original vector X?
Usually converges to like the largest vector. So any particular vector. It's the largest eigenvector if telling a square about other funky things if it's not.
Yes, lots of funky things. So yeah, so W, yeah. So let's say that W is non-funky. Like let's just say like it's a nice matrix, square matrix where you can get your eigenvectors. And then whatever is the eigenvector with the largest eigenvalue, this thing is approaching it. That's where I'm going to write this. So we're going to write V1 as the largest eigenvector. It's approaching this with some scalar, and it has to do. So it's actually there's going to be some constant there. So it's approaching this with some constant. So I'll just write a constant. Yeah. So what's happening is, X can be written as a linear combination of the eigenvector. So if W is nice, X can be written as a linear combination of the eigenvectors of W because they form a basis for the space you're in. So, X can be written as C1 blah, 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 through however large the space is. And every time you multiply by W, you get a multiplier, you get a multiple of the eigenvector, and that scalar factor is the eigenvalue. So when you multiply by W, that's what happens. And if you did this, n times, you just would get each of these eigenvalues to the nth power. So this is, oops, let's see, yeah, that's right, like that. Too many n's. So that's what's nice about, that's one of the nice properties of eigenvectors for a matrix is that it really allows you to to split up the actions of W on these eigenspaces. So what's happening here is n goes to infinity. Well, whichever of these is the largest, whichever of these lambdas, your eigenvalues are the largest in absolute value, that term is going to dominate in absolute value like the whole term here, right? So just like, say like everything was positive, like all of the eigenvectors or eigenvalues were positive, then that value is going to be, if it's largest, it's going to be eventually larger than all the rest of the values. So that's why this thing is actually, as you power this up, you get approaching some. It's going to align itself with the eigenvector. So why is that a problem? Well, what happens in this case if like your largest eigenvalue, lambda 1, what happens if it's greater than 1? Where is this? What's the magnitude of this vector approaching?
Well, the approach is infinity, but I thought we just said that it would converge if you multiply it with something.
Well, it is converging to this, like in the sense of like the difference in magnitude between these two things is going to 0. But that doesn't mean that the magnitudes of these vectors themselves are not going to infinity. So the point is the following: because you have these, you do a sequential. When you do the backpropagation, you have to do this backpropagation through each of the cells. And each time you go through the cell, you're gonna be multiplying by, actually I'm looking at the transpose W, but you get W in there. What happens is if the largest eigenvalue, or in general largest singular value, is greater than 1, then this term is blowing up. It's going towards infinity. So your gradient is becoming huge. And that's a problem. Because if gradients become huge, then you're taking like monstrous steps, and I mean, besides just like obvious like overflow issues and things like that numerically, just these things become impossible to work with. The signal, like there's just noise that begins to swamp out everything else. So that's what happens there. You can deal with this, actually. There's like, as goofy as this sounds, this actually works pretty well. People just do what's called gradient clipping. Most deep learning packages actually have this as part of their API, where you can just say like, clip this to, have magnitude 2 or 10 or whatever it is you want it to have. And you can just say like, if the gradient is too large, just cut it off and don't let it get too large. And actually, it works great, which is weird because it's like adding a whole bunch of noise just to like cut the gradient down in size. But hey, most of this is mysterious, so why not throw in a more mysterious thing? So that's how you deal with that. But what happens when your largest eigenvalue is actually less than 1 in absolute value? Or your largest singular value is less than 1 in absolute value. What's happening? This thing is approaching 0, so your gradients are vanishing. And that's not so easy to deal with. And you can imagine, like just like in the clipping where you just decided to like make it smaller, you could say like, oh, why don't I just make the gradients larger? But that actually doesn't work in practice, and mostly because like you're really amplifying noise in that case. So what do you do about this? Well, as this is implying, change the recurrent neural network architecture itself to deal with this. So, how do we change it? Well, as you might imagine, there's like lots and lots of ways you can change this, but here's one of the ones that's most successful. It's called the long short-term memory network, or LSTM. Who's heard of an LSTM? Yeah, these things are all over the place. So this is interesting. This was introduced a long time ago, 1997. All right. So let's figure out what this thing is. Yeah.
Why are we back to sigmoid and high quality?
Yeah. I wonder if someone's going to ask that. So I don't really know why, to be honest. I can tell you a couple things. So what this thing means here is like to apply, sigmoid to as the activation to everything coming out of here, sigmoid here, tangent. So here's what I can tell you about it. So sigmoids are really bad, and they are. Tangents are like also bad, like sigmoids are, but not as bad. And the reason why there's 3 sigmoids in the tangent here, well, for one reason this is old, so that's why. But the second thing is that actually the way this tangent behaves here is not so bad as the sigmoids, and as we go through the next couple of slides explaining what all this stuff is right here, the tangent actually sort of saves the day. If you made all those things sigmoids, it wouldn't be this would probably not work. But the fact that one of these activations is not sigmoid makes it work. Now, I think your real question is why aren't these ReLUs or something like that? And the answer is that, well, one is truthfully, I really don't know why it's not that. I've never seen anybody write down why, and I've never tried it myself. Well, how did you put ReLUs in there? One thing I think that does happen, or that could happen if you do that, is that these things are trying to, So I need to go to the next slide, but I'll just say, we really, for all of these things here, we really want a value between 0 and 1. We actually, these are going to all be, we're going to call these gates. These are all going to be gates for the information. So 0 means the gate's closed, 1 means the gate's open. So we actually do want something between 0 and 1. And we could imagine putting a ReLU maybe here for the tangent, but you kind of want this stuff to be, you kind of want the output to be in a compact interval. But it's only kind of. I don't really have a good answer for why you could just throw ReLU in there and see what happens. So that's all I can say. That would be a really great project. Someone should just throw a ReLU in there and see what happens. Yeah.
So that exact question is on number 3. So
What's that?
That exact question, why not put a ReLU there, is on number 3.
Yeah.
So can we just say that?
Yeah, I know it's there, but I'm just being honest with you, I don't really know the answer. Try to come up with one. I'll just tell you this. The reason, I'll tell you this. So the answer to that one there is because, I'll just tell it to you. So a ReLU is almost like multiplying by a matrix, right? It's just that it's almost linear. It's just that you cut off some of it. So you actually still get some of the possibilities of exploding gradients or vanishing gradients, because when you run your when you do backpropagation, you almost get the full matrix multiplication each time. So it still preserves that property. But it's when I say almost, I don't really know I don't really know what almost means. I guess that's what I'm admitting to you. I don't really know what a gap is there. So that's the real answer. Now you know how to answer that. That's full credit right there. If you just say it. It's almost like multiplying by it. Yeah, everybody's pulling out there. But honestly, I don't really know beyond that, and I've never done it myself. So, like I said, it might be somebody's great project to explore that and tell us why. The trouble is that you only do it for a certain network architecture for a certain data set, and you'll try to say and this is true for everything, which is what most of deep learning is like. Okay, so after getting what I don't know, let's go on to more things I don't know. So here we go. So what is going on with all of these activations being applied to things. So notice that, so what's happening is that we're getting basically a vector of values I and F and O and G for the same input and hidden state and matrix multiplication, and then these and then we apply these activations separately for this. So so what's going on here? So the point is that we're using exactly the same weight matrix to do all these things. So here's the important, when looking at an LSTM, here is the important couple of equations to pay attention to. So this is like the recurrence formula of these recurrent neural networks. So instead of just keeping track of the hidden state now, we actually keep track of two states. One is the hidden state itself, H, but there's this other state that we call the cell state. And we keep track of both. And here's how this works. So notice that G is like the vanilla neural network, right? G is a tanh applied to W HT minus 1 XT, right? That's like, if we go back to the slides for the vanilla neural network, that's what that is. So now what we have to do is figure out what all these rest of the scenes are doing. So let's start first with this line right here. So everywhere you see these funny dots with a circle, that means entry-wise multiplication. So it's like you have a vector of things here and a vector of things here, and you're just doing entry-wise multiplication. Okay, so this cell state is created in the following way. We take the previous cell state at time t minus 1, and we first multiply it by this output f. And f is what is known as the forget gate. So whether or not we should erase this cell. So basically what this is saying is like how much of this current, like of the previous cell state, should we use when we update to the current cell state? So it's a gate allowing us to go between 0 and 1 on all the entries and just say like, should we remember this, should we not? And then we add to that what we would typically get out of a recurrent neural network, G. I don't know why that's called the gate, but just the gate. You know, just like whatever, just like the plain vanilla piece. And we have this other input I saying whether or not we should, what of this should we write? Or how much of that plain vanilla output should we use in updating the cell state? So that other gate I is known as the input gate. And then we take that cell state. So it's got something from the past, and now something that we would typically get from the recurrent network. We're sort of putting these things together. And now we say, okay, let's apply a tanh to that. And instead of just calling that the update, the updated hidden state, we actually have one more gate, and that is how much of this cell state should actually be revealed in the hidden state. So you have it. You have three gates: input, forget, and output, that give you the hidden state. And like, if you're not just like, what is going on here yet, then you might not have been paying attention, because like, that just like, where does all this come from? Well, if you start to think about it in terms of computation graph, it starts, I don't know if it makes sense, but it starts to, like, you reveal some things that are useful about this, and that overcome the vanishing gradient issue that we have. So here's all, here are our equations again, but here's the computation graph. So it looks a little bit like the plain vanilla, like this was all looking the same right here, but now you have all these other pieces to it. And in particular, we're not just outputting the hidden state, we're outputting this other, what we call the self state. So we're keeping track of both these things. So what's interesting about the self state is the following. Like, even though things are coming in to affect it from down here, when you backpropagate the current self state to the previous self state, it has these are all constant. Like all these nonlinear activations, these are all constant with respect to that, like that upper line up there. So what you have when you do backpropagation is you only have element-wise multiplication, right, through this F. You don't have the multiplication by W, which is creating the either exploding gradients or the vanishing gradients. Now, all that stuff could still exist down here. Like, you could still have, like in the hidden state, you could have vanishing gradients, occurring still because like this W is still entering in like a very similar way. But at least there's like one track here of this backpropagation where that's not happening. And yeah, uninterrupted gradient flow. That, as funny as this might seem, it turns out that having this is known as like an information highway. Actually, it's not the World Wide Web, but this is known as information highway up here. This is allowing for information to be passed from current cells to previous cells in a way that is not affected by this blow up, by these exploding or vanishing gradients. And we've seen this actually before, although we didn't really put it out this way. Anybody recognize like something similar here? Things that we've done in the past with convolutional networks? Yeah. This is a lot like a residual network. So these skip connections, so you have all this like so remember in the residual networks we had these blocks where you had like nonlinearities happening, nonlinear, we had your typical layers, linear maps, nonlinear activations, you stack those up. But then you had these skip connections that were just basically like the identity maps going from here to here that allowed you to basically, it allowed a couple things. Like you could learn nothing. You could literally have vanishing gradients here, like very small gradients. But from this contribution, but you would still have plenty of gradient coming from the identity map to allow you to learn very, very deep networks. And a similar principle is happening here for these LSTMs because of the way that the self state, the C, is backpropagated in these computation graphs. And again, like these highway networks, or this LSTM is an example of like a general class of networks called highway networks that use this kind of idea of like low burden computation to preserve some gradient information to pass on. And this allows you to train really deep networks. Because like you need, if you're going to learn to like translate from, if you're going to learn to predict, it doesn't even need translation. Like if you're going to learn to predict or to generate text that is very believable and like allows for very long-term temporal relationships between like, say, two characters through a script. Like you need to be able to have very, like when you unroll this template, you need to be able to have very deep networks. Like you need to have many, many time steps or many steps in your sequence, which translates to depth in your network. So you need, just like in the residual networks, to get very deep convolutional networks, you need something that allows information to continue to propagate even when, say, otherwise good. So this is a solution to that problem, even though you might still like be thinking, how is that a solution to this problem? But truly it is. And it turns out though, like LSTMs aren't the only options here. There is another pretty popular recurrent neural network that also solves this problem in a slightly different way. It's called a GRU, a gated recurrent unit network. And here is the basic update equations for that. We won't concentrate on this one in this class, but you'll see GRUs often as well, although LSTMs seem to be the most popular when thinking about recurrent neural networks. You can see that this has a similar strategy for like gating certain information off the state. What this does instead of let's see. So this has a couple different parts to it that are a little bit different. Like there are biases when we haven't had biases before, but that doesn't make that big of a difference. But you have like instead of having like the self state that's a bit independent of the hidden state, you keep like this. You keep this like prior on the or like a pre-hidden state, and you combine that with the previous hidden state. Using this output from Z. So it's like a value between 0 and 1, and you just combine it in that convex way. Anyways, you'll see these often as well. They're similar, but yeah, there's no reason why you wouldn't use one or the other. In fact, like a lot of papers that are like putting networks together like this, they'll often try they'll try both. They'll say, hey, we did better with LSTM or we did better with GRU, so we went with that. That's really what it comes down to. Okay. So summarizing all this. So RNNs. Yeah, they allow for a lot of flexibility in architecture design in terms of like, how many inputs to how many outputs. These vanilla RNNs are simple, but they don't work very well, mainly because you can't learn very long-term relationships. As you start to learn longer-term relationships, your gradients they either explode or vanish, and so it makes it very hard to learn long-term relationships. So like, if you were just learning like to predict the next letter from say like 2 letters or 3 letters, like this would work, quote unquote, like you could train, but this wouldn't produce a very interesting model, right? Like it wouldn't, like the things that it would produce wouldn't really feel like language to you. So you need something that can deal with longer-term relationships, and that's what the LSTM is about, or GRU. And so this part here about better, simpler architectures are a hot topic of recurrent research. I mentioned attention. Attention is replacing recurrent neural networks is like a really significant topic of research right now. And, I mean, who knows where that will end up, but it's pretty impressive. And like with most things here, like this is really true. Like, who are the mathematicians in this room? Yeah. Are any mathematicians frustrated by the lack of theory? Yeah. Who are the computer scientists in the room? Are any of you frustrated by the lack of theory? Some of you are. Yeah. This is such a funny topic for this very reason. Like these things work and they work great, and like they can do lots of really, really interesting things. But like why a particular network works or not, or like why like certain adjustments, like why the LSTM over like all the other ways you could do this, it's not really that clear. It just there's some understanding as to why it should work and like what it overcomes, but it's not at all clear that that's like an optimal way to solve the problem. It just is a way that solves the problem and solves it really well. So, and I hopefully just I don't know what else to say about that. So even in that question that's asked in the homework that I gave you the answer to, like even that is like kind of like a not fair question because of the almost part of what I was saying. It's just like like these are reasons why we expect it to, like why we expect this doesn't work that well, but like really like looking at a paper that, or like in a textbook that was like, this is why it doesn't exist. So, yay. All right, so that's it for today. I'm happy to answer any more questions or you want to find out questions.